In the last lecture, we saw what is trigonometric Fourier series expansion, and now in this presentation we will solve one example. You can see the waveform on your screen. It is a rectangular wave, and this waveform is the waveform of signal xt, and we are required to express signal xt in terms of its harmonics, and we can do this by the help of trigonometric Fourier series expansion. So first I will write down the expansion, and then we will analyze the given waveform to reduce our calculations. Signal xt can be written as sum of DC value or the average value of the signal, which is represented by a sub 0 plus all the cosine terms. So we have summation n equal to 1 to infinity a sub n, which is the Fourier coefficient cos n omega naught t, plus all the sine terms, so n equal to 1 to infinity bn, which is another Fourier coefficient multiplied to sine n omega naught t. So this is the expansion, and now we will analyze the given signal. You can see the given signal is symmetrical about the time axis. This means when you calculate the area in one time period, you will find it is equal to 0. The positive area will cancel out the negative area, and therefore we will have 0 as the total area in one time period, and therefore when you calculate the average, when you divide the total area by the fundamental time period, you will find it is equal to 0. So the average value or the DC value of this particular signal is equal to 0. So we can say A naught is equal to 0. So there is no need to calculate the A naught. Now you can see the given signal is also mirror image about the y-axis. And when this happens, the given signal satisfies the condition for even signals. This means when you perform the time reversal, when you find x minus t, you will find it is equal to xt. So when you fold the signal about the y-axis, you will have the same signal, and in that way we can say that xt is an even signal. And whenever we have even signal, there is no need to calculate bn because there will be no sine terms. So bn is also equal to 0, and thus there will be only cosine terms present in the expansion of signal xt. So we can rewrite the expansion like this. Xt is equal to summation n equal to 1 to infinity a sub n cos n omega naught t. So our main task is to calculate this coefficient an. Once we have an, we can substitute it in the expansion, and we will have the Fourier series expansion of signal xt. So I hope you now understand what is the use of analyzing the given signal before performing the calculations. Even if you perform the calculation for A naught, you will find it is equal to 0. So you will end up wasting your time. The same thing goes for Bn in this case. When you calculate Bn, you will find it is also equal to 0. So always try to analyze the given signal before performing the calculations. Now we will move on to calculation of An. We already know the formula for An. It is equal to 2 over fundamental time period t naught integration signal xt multiplied to cos n omega naught t, and the range of integration, you can take any range, but it should be over the fundamental time period t naught. For example, in this case I have taken this structure. This structure is repeating from minus infinity to infinity, and if you see the fundamental time period, you will find it is equal to 4 seconds. If this time t is in seconds, you will find the fundamental time period is from minus 1 to 3, and it is equal to 4 seconds. In the same way, if you take some other structure, for example, if you take this structure here repeating, then in this case the structure is starting from minus 3 and it is ending at 1. So you can clearly see again the fundamental time period is equal to 4. You can easily find out the fundamental time period by subtracting minus 3 from 1, you will find it is equal to 4. The same way we calculated the fundamental time period 4, in this case, subtracting -1 from 3. So 3 minus -1 is equal to 4. So carefully select the range of the integration. You cannot take the range -1 to 1 because this structure is not repeating from -infinity to infinity. Now let's move to our calculation. First we will calculate omega naught, which is the angular frequency, and we can calculate the omega naught because we know the value of fundamental time period t naught is equal to 4 seconds, and we know omega naught is equal to 2 pi over t naught, or we can say 2 pi over 4. So omega naught is equal to pi by 2 radians per second. So we have omega naught, we will substitute omega naught here, and we also know the value of t naught. So in the next step, I will write down an as 2 over 4, which is 1 over 2. Integration, the range of integration is -1 to 3. So we have -1 to 3 xt multiplied to cos n pi by 2 t dt. Here we have dt. So this is what we have, and now we will perform this integration. I will explain each and every step in great detail. I will not skip any point because this is our first example. So let's calculate the result of integration. 1 over 2. I will split the integration in two integrals because we have signal value xt different from -1 to 1 and from 1 to 3. You can see in the signal waveform from -1 to 1 signal value is equal to 1, and from 1 to 3 signal value is equal to -1. So the first integral will have the range -1 to 1, and the value of signal xt is 1. So we have 1 multiplied to cos n pi by 2 t dt, plus the second integral will have the range 1 to 3, and value of signal xt is -1. So -1 multiplied to cos n pi by 2 t dt. Now we will solve the two integrals. An is equal to 1 by 2 integration -1 to 1 cos n pi by 2 t dt, minus this minus I have taken out, integration 1 to 3 cos n pi by 2 t dt. Now we will assume n pi by 2t as theta. To perform the integration, we will assume n pi by 2t equal to theta, and to find out the very small value of theta, we will focus on t because n pi by 2 is a constant. So if we have n pi by 2 very small t, we will get very small theta, which is d theta, and from here we can say dt is equal to 2 over n pi d theta. And as we are trying to have theta in place of n pi by 2t, it is important to change the limits as well, because -1 here is the value of time t. So let's try to have theta when t is equal to -1, 1 and 3. So when t is equal to -1, we have theta equal to minus n pi by 2. Put t equal to -1 here and you will have theta equal to minus n pi by 2. In the same way, when t is equal to 1, we have theta equal to n pi by 2, and when t is equal to 3, theta is equal to 3n pi by 2. Now we will substitute all these values in the integration. An will be equal to 1 by 2 integration. In place of -1, we will have minus n pi by 2. So we have minus n pi by 2. In place of 1, we will have n pi by 2, n pi by 2, cos n pi t by 2 is equal to theta, so we have cos theta, and dt is equal to 2 by n pi d theta, so 2 by n pi d theta. Similarly, we have integration n pi by 2 to 3n pi by 2 cos theta 2 over n pi d theta. 2 over n pi is a constant, so we will take it out of integration, and 2 over n pi is common in both integrals. So we have an equal to 1 by 2 multiplied to 2 over n pi, which is the common term in both the integrals, and inside the bracket we have integration minus n pi by 2 to n pi by 2 cos theta d theta minus integration n pi by 2 to 3n pi by 2 cos theta d theta. And we already know the integration of cos is equal to sine, and the differentiation of cos is equal to minus sine. So integration of cos theta is equal to sine theta. So we have an equal to 1 by n pi. This 2 and 2 will cancel out, so we have 1 over n pi. Integration of cos theta is sine theta. The lower limit is minus n pi by 2 and the upper limit is n pi by 2. And again the integration of cos theta is equal to sine theta. The lower limit is n pi by 2 and the upper limit is 3n pi by 2. Now we will put the lower and upper limits and we will see what we have. First we will deal with the result from the first integral, and we will have sine n pi by 2 by putting the upper limit. Then we have minus sine minus n pi by 2. Then we have sine 3n pi by 2, and then we have minus sine n pi by 2, and because of this minus will become plus. So this is what we have. In place of theta we have substituted the upper and lower limits. Now we will focus on the middle two terms. We will focus on sine minus n pi by 2 and sine 3n pi by 2. So first we will talk about sine minus n pi by 2. For this you should know about the basics of trigonometric ratios. This is 0 degree, 360 degree, this is 90 degree, this is 180 degree, and this one here is 270 degrees. This is the first quadrant, this is the second quadrant, this is the third quadrant, and this one here is the fourth quadrant. In first quadrant all the trigonometric ratios are positive, so I will write all in the first quadrant. In the second quadrant sine and cosec are positive, so I will write sine here. In the third quadrant tan and cot are positive, so I will write tan here. And in the fourth quadrant cos and sec are positive, and you can remember it as all silver tea cups. To understand this I will take one example. In this example we have sine pi by 2 minus theta. Pi by 2 means 90, so we have 90 minus theta. 90 minus theta means we are in first quadrant, so the sign we are going to get is positive, because in first quadrant all the ratios are positive. Now as we are having pi by 2 here, sign will change to cos, so we have cos theta. Very simple. Let's take another example. In this example I will take sine pi minus theta. Pi minus theta means we are in the second quadrant. 180 minus theta is between 90 and 180 degrees. Therefore we are in second quadrant, and in second quadrant sine is positive. 180 degrees plus minus anything, sine will not change to cos, it will remain sine, so we have sine theta. So sine pi minus theta is equal to plus sine theta. So in this way we have to use the quadrants, and this shows the actual variation of sine, cos, etc. with change in angle. Now we will focus on sine minus n pi by 2. I can write sine minus n pi by 2 as sine 0 minus n pi by 2. 0 minus something will lie in fourth quadrant, and in fourth quadrant cos is positive and sec is positive. But here we have sine, so we have negative sign, and as we are having 0 minus something, sine will not change to cos. So we have sine n pi by 2. So overall we have minus sine n pi by 2 in place of sine minus n pi by 2. So we are done with the second term. Now we will focus on the third term, which is sine 3n pi by 2. I will change the color of my pen. Here we have sine 3n pi by 2. I can write it as n pi plus n pi by 2, which is nothing but sine 3n pi by 2. Now when n is even, we have some different result. When n is odd, we have some different result. So we have to focus on two different cases. In case number 1, when n is even, n pi means 360 degrees. For example, when n is 2, we have 2 pi, which is 360 degrees. When n is 4, we have 4 pi, which is nothing but 2 times 360 degrees. So it means 2 revolution, and again you are at 360 degrees. So when n is even, we are at 360 degrees, and 360 degrees plus something moves us in the first quadrant, and in first quadrant every trigonometric ratio is positive. So we have sine n pi by 2. Sine will not change to cos because we are at 360 degrees. Sine will change to cos only when we have 90 degrees plus minus something, or 270 degrees plus minus something. So when n is even, in place of sine 3n pi by 2, we can have sine n pi by 2. Now we will discuss the next case, case number 2, in which we will consider n to be odd. So I am writing case number 2 here. In this case n is odd. When n is odd, let's take one example. Let's say n is equal to 1. We have sine pi plus pi by 2. Pi means 180 degrees, and 180 degrees plus something moves us in the third quadrant, and in third quadrant sine will become negative. However, sine will not change to cos. So we have minus sine n pi by 2. So when n is odd, we have minus sine n pi by 2 in place of sine 3n pi by 2. Considering these two important points, we will write down an, and this time we will write it down for two different cases. In case number 1, we have considered n to be even. So we have an equal to 1 over n pi inside the bracket sine n pi by 2. In place of sine minus n pi by 2, we have minus sine n pi by 2. This negative sign was already there, so we have plus sine n pi by 2. In place of sine 3n pi by 2, we can write sine n pi by 2. Negative sign was there, so we have minus sine n pi by 2, and this sine n pi by 2 will come as it is. So you can see we have sine n pi by 2 cancelled out, and we are left with 2 times sine n pi by 2 multiplied to 1 by n pi. So an is equal 2 over n pi sine n pi by 2. Now again you have to focus on very important point. Here n is even. Now try putting something even here. For example, let's take n equal to 2. Let's take n equal to 2. This will give us an equal to 2 over 2 pi sine 2 pi by 2, or we can write an is equal to 1 over pi sine pi. Sine pi is equal to 0, or you can say whenever you have sine n pi, it is going to be 0, and whenever you put n something even, you will get the integral multiple of pi. So every time you are going to get an equal to 0 if n is even. So an is equal to 0 when n is even. Now we will consider the case number 2 in which n is odd. So let's move to case number 2, and in this case n is odd. For odd we have again two different cases. Let's call the first case case A. In this case n is 1, 5, 9, 13 and so on, and in case B n is equal to 3, 7, 11, 15 and so on. I will explain why we have taken two different cases when n is odd. Let's discuss the first case when n is 1, 5, 9, 13 and so on. In this case an will be equal to 4 over n pi. It is equal to 4 over n pi because we can clearly see from here an is equal to 1 over n pi sine n pi by 2, sine n pi by 2. Sine minus n pi by 2 is equal to minus sine n pi by 2. Negative sign was already there, so we have sine n pi by 2. Now there is difference if you compare the third term in case of even and in case of odd. In case of odd we have sine 3n pi by 2 equal to minus sine n pi by 2. Minus sign was already there, so we have plus sine n pi by 2, and this term will come as it is, sine n pi by 2. So from here an is equal to 4 times sine n pi by 2 multiplied to 1 by n pi, or we can write 4 over n pi sine n pi by 2. And when n is 1, 5, 9, 13 and so on, we will have sine n pi by 2 equal to plus 1, because we know sine pi by 2 is equal to plus 1, but sine 3 pi by 2 is equal to minus 1. And the same way the cycle will repeat itself. So whenever we have 1, 5, 9, 13 and so on, this sine n pi by 2 will become plus 1, and whenever we have n equal to 3, 7, 11, 15, this sine n pi by 2 will become minus 1. So an will be 4 by n pi for this case, and an will be minus 4 over n pi for this case. So we have everything to substitute in our expansion, and after analyzing the given waveform, we have seen a0 and bn is equal to 0. So xt is equal to summation n equal to 1 to infinity an cos n omega naught t. Omega naught is equal to pi by 2, so we have cos n pi by 2 t. Now we will expand it by putting the different values of n. First we will find out the value when n is equal to 1. When n is equal to 1, an is equal to 4 by n pi. N is equal to 1, so it is good to call an as a1, and a1 is equal to 4 by 1 into pi. So 4 by pi, and here we have cos pi by 2t. Cos pi by 2t. After this we will find out the value when n is equal to 2. When n is equal to 2, we have already seen an is equal to 0 because n is even. So 0 multiplied to cos pi t will be equal to 0. So we will only focus on the odd values from now. So when n is equal to 3, you can see an is equal to minus 4 by n pi. And as n is equal to 3, it is good to call a3, and it is equal to minus 4 by 3 pi. So here we have minus 4 by 3 pi, and cos n pi by 2t will be cos 3 by 2 pi t. In the same way we will find out the value when n is equal to 5. It is equal to plus 4 by 5 pi cos 5 pi by 2t, and when n is equal to 7 we have minus 4 over 7 pi cos 7 pi by 2t and so on. You can see 4 by pi is common in all the terms, so we will take 4 by pi common, and inside the bracket we will have cos pi by 2t minus 1 by 3 cos 3 pi by 2t plus 1 by 5 cos 5 pi by 2t. After this we have minus 1 by 7 cos 7 pi by 2t, and so on. So this is our answer. This is the expansion of signal xt using the trigonometric Fourier series expansion. And you can see we have different harmonics in this expansion. So this is the complete process to find out the trigonometric Fourier series expansion. The only important thing is the integration. You can see if you do not know how to perform the integration, you cannot have this result. So this is all for this lecture. There is one thing I want to change here. If you remember, I told you whenever we have integral multiple of pi, sign will become 0. I have used n here, which I don't want to use. I will use m in place of n because it will create some confusion. So we have sine m pi equal to 0, where m is some integer. So whenever you have n as even, here n as even, n divided by 2 will give you some integer. For example, 4 divided by 2 is 2, 6 divided by 2 is 3. So whenever you have even value of n pi, there will be integral multiple of pi, and for this sign is equal to 0. So this is all for this lecture. If you have any doubt, you may ask in the comment section. I will end this lecture here. See you in the next one.